Today we are truly honored to have Martin Lettau as our kickoff speaker. Martin is a professor in the Haas Business School. If I were to start in on his resume credentials, it would take us all the way through the hour and a half, so I won't do that, but we'll rather let you enjoy his topic, high-dimensional factor models and the factor zoo.
Well, thank you so much. Thanks for coming. We're happy to be here to present this paper. So this is, the title suggests, a paper on the factor zoo. It's Cochrane's term to describe this sort of ever-growing list of characteristics that are linked to return premium, right? We start out with value growth and momentum, and now now there are hundreds of different characteristics. And obviously, we would like to have a model that is sort of more parsimonious. So the factor zoo challenge is to sort of figure out which of these characteristics really matter, right? So set the stage. Suppose we have a large number of C characteristics, okay? We observe M assets, right, over time. And the goal is to come up with a more parsimonious model, let's say with KC factors, where KC is significantly smaller than the original C pricing factors or the C characteristic sorts. So the standard approach that most papers in this literature follow is as follows. So we select a number of characteristics, right? Nowadays it's easy. There are many websites that you can download them. And then we take these characteristics. We every, let's say, month, we sort assets into each of the characteristics, maybe univariate sorts, bivariate sorts. At some point, you don't have enough stocks to go deeper in that. You form here, let's say, decile portfolios. So we have 10 C decile portfolios, and then we form the high minus low. So 10 minus 1 factor, right? So here HML does not refer to the book to market from a French HML. So for now, HML will denote the sort of generic high minus low, factor. Okay. So once we have this, let's say, very large dimension, so C is very large, we have C factors, right? And then the factor zoo challenge is to reduce the dimension from this large number of C characteristic factors to a smaller number of KC factors that, in the end, are deemed to be, relevant and forms of the true, in quotes, true pricing model. And the literature focused obviously on the second step, right? So dimensional reductions. So a lot of the, nowadays fancier models are about step 2, right? So we can start with something simple. PCA is sort of the standard going back many decades. There's a lot of work on extensions of PCA. Then we get into like lasso-rich kind of models, machine learning, neural nets, random forest, and so on. So there's a very large literature that sort of addresses this factor zoo, given that we have a large number of characteristics. So in this paper, I will propose a different approach. Essentially, I'm going to reverse the order. Okay. So instead of first sorting and then sort of figuring out the factor zoo dimension reduction in the return space, I will first address the factor zoo in the characteristic space. So instead of having these C characteristics, I will form characteristic factors in KC, where KC is much smaller. So the model that I will use reduces the dimensionality in the characteristic space. So instead of having C characteristics, I end up with KC characteristic factors. And then once I have these factors, then I can treat them just like the original factors, and I can sort, and I can form portfolios, and then high minus low portfolios. Right? So the difference is here, the dimensional reduction is in the return space. Here it is in the characteristic space. Okay, that's the difference. Okay, so I will reverse the order. Yeah. So that's what that's what the paper is all about. So we want to resolve this factor zoo challenge here in the characteristic space. That's sort of the general approach. So the challenge is that the data is three-dimensional, right? So we observe many characteristics of many assets over time. So how can we do dimension reduction in a three-dimensional data set? Okay, and obviously there's information along each of the three dimensions, right? So for example, for a given fund, book to market earnings to price are correlated. Across similar stocks, the book to market ratio will be correlated. And of course, there's correlation over time. Okay, so we want to capture the correlation information in all of these three dimensions, right? However, standard models, PCA and factor models, really apply to only to two dimensions. So one thing we could do is we could eliminate one dimension. We would lose some information, obviously, and then just apply PCA and factor models along the two dimensions that we chose. So the model that I will propose applies to three dimensions directly, right? So formally, a higher dimensional object is called a tensor, right? So you go from a scalar to a vector to a matrix, and then to a tensor. So the simplest tensor would be a three-dimensional cube, essentially. Okay. So what I will use sort of factor models that can be applied to tensors directly. Okay. So the advantage, obviously, is that these models exploit dependencies in all three dimensions simultaneously. So there's no need to sort of eliminate one dimension and lose information. And also it allows for complex dependency across characteristics. So one problem with this sorting into characteristic factors is we can at most probably do a univariate or bivariate sort, not more than that. So that limits the interactions of different characteristics. So essentially the geometrician has to decide, okay, I'm going to either do univariate sort, or I might do a bivariate sort of each characteristics and size. So this has to be determined by the geometrician. Okay. In contrast, the tensor factor model allows the data to decide and allows much more complicated and complex dependencies across characteristics. So the methodology in this paper has sort of three parts. So first, I will use these tensor factor models to reduce the dimensions in the characteristic space. That will be the first half of the talk. The second half will be then the asset pricing piece. So once I have these characteristic factors, I will construct these asset pricing factors that come out of the tensor model. And then once I have those, then I can use the standard battery of asset pricing tests that we are all familiar with. Okay, so I can essentially compare these factors from the three-dimensional factors with benchmark models like French factors, PCA factors, and everything else. Okay, so that's sort of the outline of the talk. So what are the main findings? So I find that these tensor factor models actually work tremendously well. Okay? So for example, very parsimonious models capture over 90% of the data while compressing the data by more than 95%. So they're very efficient ways to compress the data while still capturing most of the variation in the data. Okay? So you don't have to take, by the way, you don't have to take pictures. If you want the slides, just email me. Okay, so there's no need to take iPhone pictures of these slides, right? You know, in general, if you're a student and you go to a presentation, it's a conference or here, don't take pictures, just send an email to the presenter and they'll be happy to do that. And it's much easier to work with, okay? So, so these models really are very efficient ways to compress the data while still capturing most of the variation. So, the paper goes into a lot more details about the fit. I don't have time to do this. So one of the maybe most interesting aspects is it's a good fit for most characteristics, but the the two characters that are hardest to fit are momentum and reversal, right? Which maybe is not surprising. I will, if I have time, go into a little bit more detail. These models are stable over time. I get very robust results. So that's the first part. And then the second, the asset pricing part is I find that these factors that come out of these models actually have higher returns and Sharpe ratios than so standard PCA factors. I'm not sure why the menu popped up. And I find that they are actually related to the cross section, and they actually also use smaller pricing errors than the benchmark factors, like Parsimonious French and PCA factors. I might have pressed something.
No, someone commented in the chat.
I see. Okay. So so they actually do better in the cross-section asset pricing test than benchmark models, and I find robust in sample as well as out of sample results. So that's the summary of the paper. So there's a lot of ground to cover because my experience. Oops. Oh,
yeah, you just
are we stuck now?
see, no, just press once, and I think now it should work.
Yeah, thank you. So I will skip the outline. There's a lot of ground to cover, especially because most people in the audience that I present to are not familiar with tensor models, right? So I will give you the intuition, and the details are in the paper. Okay. So it's actually not that difficult. It's sort of, you have to get used to it because a lot of the algebra in 3 dimensions is just something that we don't usually do. So just in terms of notation, so a scalar will be like a lowercase letter, vector will be a bold letter, a matrix will be a uppercase letter, and any tensor will have this script, So I will only talk about the 3-dimensional case, but everything extends to higher dimensions. Okay, so I will only work with 3 dimensions. It just makes the notation much easier.
So the dimensions we have in mind are characteristics.
Yes, so
Time
and assets.
and assets.
So it's a cube,
Uh-huh.
right? Where the first dimension will be time, the
Yeah.
second dimension will be assets, and the third dimension will be characteristics. Okay, so that's sort of the.
Keep this in your head while you write
That's
the
so
abstract
I will denote in the future. I will denote these these dimensions as T, M, and C.
Mhm.
Okay, so instead of using 1, 2, 3. It's easy to follow. So T will be the time dimension, the first one, second will be assets, and third one will be characteristics.
Why are assets called M?
Because in the application, I will use mutual fund data.
Mutual.
I will, but
Got
in
it.
principle,
Thank you.
I mean, for now, it's
No,
just assets.
Super
right?
helpful. Thanks.
So that's why it's M. But for now, it could be stocks, could be anything. I'll talk about the sample later on. Okay. So one way to sort of think about tensors, then you can sort of look at, slice and dice them. So fibers or the vectors that make up this cube are called fibers, right? So they are fibers in each of the 3 dimensions, depends on how you slice and dice them. And the matrices that make up the tensors are called slices, right? And again, you can slice the tensor 3 ways, right? So they are sort of 3 sets of fibers and 3 sets of slices. So the only really notation that I will use is the tensor multiplication when I multiply a tensor by a matrix. So one thing you have to get used to is that for tensors, there's no transpose operator. Okay, so because there's no unique way to rotate the tensor. So everything when you multiply a tensor by a matrix, you have to indicate which dimension you're multiplying by. So for example, here, this is the tensor. We would multiply the first dimension by the matrix A1, and then the second dimension by the matrix A2. And they have to have conforming dimensions. Okay, so the way this tensor multiplication works is that you multiply each n-dimensional fiber or vector by each row of the matrix. I will show you a picture in a few slides. So that's sort of for this talk the only thing tensor operation that I need. Okay. So the data is again three-dimensional characteristic C of asset M in quarter T. So it should be T here. So what is the intuition of this tensor factor model? Well, so the objective is to summarize the information in a small number of factors. So one thing we could do, we could just eliminate one dimension and do PCA. So for example, we could do a two-dimensional PCA for each period, right? For the first period, we have a matrix of characteristics across assets in that period. So we can estimate T two-dimensional PCAs, right, for each of these slices in that dimension. We could also do PCA for each asset, right? We slice it in the M dimension, so we have M separate PCA models. And then finally, we can also slice it in the characteristic dimension and then estimate C, independent or separate factor model, right? So that's one way to sort of eliminate one dimension. So these models, so we have T plus M plus C factor models, but each only exploits two dimensions, right? So if you do it by time, you will lose all time information because you do time by time. If you do it, if you do asset by asset, you lose information because obviously there's correlation across assets. So none of this doesn't seem very sensible, and you certainly lose information. Yeah. Another issue is that the order of factors might change. So for example, if there's a book to market and a size factor, for some assets, the size factor might be second, the book to market might be third, and for others it's flipped. So this can be inconsistent as well. So the intuition of the tensor factor models is that essentially it's an estimation of this T plus M plus C separate PCA models, but estimated simultaneously at once. So it's one step. You estimate only one structure, and that captures all these T plus M plus C two-dimensional PCA models. That's the intuition of the tensor factor model.
I have a question, and the two-dimensional ones I'm used to.
Yeah.
There's statistical interpretations
Yeah.
to some variables like return.
Yep.
We impose that it's true, but we think of it that way. And others might be just stuff we observe, like characteristics, which also maybe it vary kind of slowly, at least in some cases.
Well, some do, some don't.
For some do, some don't, for some securities at some times, but it doesn't really have a statistical interpretation that I'm used to.
So let me,
You'll
you'll see that. I will give you the intuition,
Yeah.
not the more details, but the intuition.
Thank
Essentially, we'll see. I mean, essentially, these models are direct three-dimensional extensions of PCA / singular value decompositions of matrices. Okay,
Yeah.
so they have the same intuition and also the same properties. So it's essentially you estimate this T plus M plus C two-dimensional factor models simultaneously. So they're all connected and they are subject to restrictions, and the paper works out what these restrictions are. Okay? And again, the advantage is here, this model will exploit correlations or dependencies in all three dimensions simultaneously, so you don't lose any information. So just some notation. So let's go back to the two-dimensional case. Let's just set the stage. Okay. So, for example, we can we have a data matrix X. Okay, two dimensions. We can compute the K factor, so the truncated SVD, right? And then the SVD approximation to the data will have this form. Well, where H is the diagonal matrix of eigenvalues, and U1 and U2 are the eigenvectors of X times X prime and X prime times X. Right, and so once we have the singular value decomposition, this implies a factor representation, right? So essentially, this would be the factors, this would be the loadings matrix, right? This is the standard PCA that we are all familiar with. Okay, so the factors would be formed by the eigenvectors and the eigenvalues, and then the U2 would be the loading matrix, right? So this would be a T by K matrix, and this would be a K by, say, N matrix, right? So the Tucker decomposition essentially extends this matrix SVD to 3 dimensions. That's really all it is. So just to avoid confusion, for now, when I say factor, I refer to PCA or tensor factors, not asset pricing factors yet. Okay, so until we get to the asset pricing piece, when I say factor, I always mean so factor like a PCA factor or a three-dimensional factor. Okay, just to avoid complications. So this is the standard, standard plot here, right? So if we have our data as a 10 by 5 matrix, and we have a two-factor or two-dimensional PCA or SVD with 2 factors, right? Then U1 is a 10 by 2, 2 by 2, and 2 by 5. Right? We all know that. Now, so note that in principle, we could write the SVD where we have a different number of factors in this first and second dimension. Right? So if we, for example, have an SVD with 3 factors in the first dimension and 2 in the second dimension, then here I would have a 10 by 3 matrix, a 3 by 2 matrix, and then the 2 by 5 matrix. I could write it like that. However, because H is diagonal, these 2 elements are 0, right? And this will reduce to the case where with 2 factors on both sides. So the reason that we have the same number of factors is because H is diagonal. Okay? So one key aspect of the tensor extension is that what is similar to H will not be diagonal. Okay, so therefore, we will have different number of factors in each dimension. Okay, so that's the one difference that for the tensor case, we will have a K1, a K2, and a K3. So a different number of factors in each dimension. And the reason is that what will replace H will not be diagonal, right? So the reason is that for the SVD, this is the matrix of eigenvalues. Tensors don't have eigenvalues. So the corresponding decomposition, this will not be diagonal. So the two-dimensional case is sort of special because this is related to eigenvalues and eigenvectors. Right? This only holds for the two-dimensional case.
Martin, in the two-dimensional case, I mean, the SVD will give you an exact.
No. No.
No?
Yes and no. That's the K factor, right?
Yeah.
So in principle, if you want to have the exact, this is the error term. So you want to have a low rank factor model.
Right. So
if you have a full rank SVD, then you would have, right?
And to get to so the analog with the two-dimensional cases, you use Marchenko-Pasteur to figure out which are the singular, which are the most important eigenvalues.
Well, so that goes back to the 20s. Yeah. Essentially, you can show that the optimal choice would be to use the eigenvectors and eigenvalues that correspond to the 2 largest eigenvalues.
Yeah, right? In this case, yeah.
In this case.
Yeah. But in a more higher dimensionality case, you could apply Marchenko-Pasteur and reduce the matrix, and you have an estimation error. But
I mean, here you also have an estimation error if K is smaller than the dimensions.
Yeah.
Right.
Yeah.
So if the data, for example, is 10 by 5, and I want to have only 2-factor model. Yeah. That's why it's an approximation. Yeah. Right. And the optimal UH and U1, H, and U2 would correspond to the first 2 largest eigenvalues and eigenvectors.
Got it.
Okay.
Okay.
So, but there's the full rank SVD. This would be 10 by 5.
Yeah.
5 by
5.
Yeah, and then right? So
Yeah.
you would,
And then
this is
Yeah.
the
Okay, this
approximation,
would be
right?
lower
you've
dimension.
you've just truncated out
It's
stuff
called a
that
truncated SVD.
that you've decided is
Exactly.
not driving correlation,
Exactly, right, and then you do the usual thing, right?
right? But that's
So-
the judgment. you
Right,
make.
so, and the reason why we only have one K is because if you had different number of Ks, it would use to the minimum of the two K.
Okay, okay,
So here's the corresponding picture for the, what's called the Tucker decomposition. So the Tucker decomposition extends the SVD to tensors. So let's say we have a large data tensor. So here it's 6 by 5 by 4. That's our large data tensor. Okay. So then we have something called what's called the core tensor. It's a small tensor. Here 3 by 2 by 2. This will be the dimensions that I'm choosing. So there's 3 factors in the first and 2 factors in the second and third. Okay. So the idea is that the core tensor is sort of a compressed version of the large data tensor. Okay, this will correspond to the H matrix in the SVD.
Mhm.
And then all I do is I multiply the tensor by what's called a loadings matrix, V. So VT is the first loadings matrix. It's 6 by 3. So essentially, if you multiply this tensor by that matrix along the first dimension, the dimension changes from 3 to 6.
Yeah, 6, which is.
Right, and the way you do it, you multiply each row by each of these vectors, right? And then when you multiply it out, this will be a 6 by 2 by 2. Okay, so this will be the first part of the SVD. This is like U1 times X. So this is like G, and this would be the VT here. So note that I switched from 1, so the VT is the first dimension. Okay, and then I do the same thing for the other 2 dimensions. Right? So this is 3 by 2 by 2. I multiply the second dimension by this 5 by 2 matrix. Right, and
2 by 5.
5 by 2. So it's you multiply. So here you multiply.
2 is
This-
the number of row.
Right. So it's
Okay, now I'm
So it's-
happy.
that's why it's so the way this tensor multiplication works is that to be conforming, this 2 has to be equal to that 2.
Do you have a transpose in there?
No, you don't.
Oh,
That's the point, right? But if you multiply, like you don't have transposes here, no transpose ever. So if you multiply, so this is a vector, and this is a vector. So you would multiply each of these vectors by these by the columns of the. Okay, this takes time to get used to. It took me a while to. We don't think in 3 dimensions, but essentially, this is just, and you do the same thing here. You really have to visualize this and write it out to really get it. Okay. So this, if I multiply this core tensor 3 by 2 by 2 by these 3 matrices, I go from 3 to 6, from 2 to 5, and from 2 to 4, which is the same dimension here as the original. Okay.
okay, so now I'm gonna try one more time. In the 6 by 3, 6 is like your number of columns, and 3 is like your number. 6 is like your number of rows, and 3 is like your number of columns. And in the VM, 5 is like your number, the first number is your number of columns, and 2
Right.
is your number of rows, and that
So-
is why I'm confused.
Exactly. So
Why are the meanings of
way
those numbers different? in
because the
each
way
case?
it's written, we don't have transposes. Here I just essentially, the way it's plotted, I rotate the matrix so it matches the corresponding picture in the tensor. Okay, so this is not V transpose, this is just V.
It's
Right.
true, but it looks to me like 5, in the 2 cases, it looks to me like the first number means
Okay.
the number of columns in the second
Okay.
case and the number of rows in the first case.
Imagine you rotate, just in the picture, you rotate everything this way,
Yeah,
and this would be here, and then you would have the same. Right, so it's the way it's written and the way it's displayed is different, right? You display it so you have the correct dimensions lined up. But the way it works is that you multiply each of these vectors by these.
right,
Okay.
I'm there with you on that part, I still don't understand the labeling, okay,
Sorry,
I still don't get the labeling, but that's okay.
that's the way it's done in the tensor literature. It's the standard way, right? So the way you write this product is G. Then you multiply the first dimension by VT,
Mhm.
the second dimension by VM,
Mhm.
and the third dimension by VC. Now, just 1 second. This might be informative. If you go back to the SVD, this is the way the SVD is written. I can write this in tensor notation. This matrix product will be this product in tensor notation. These are identical. Okay, so the way we write it, you don't have a transpose here. So instead of transposing it, you're indicating which dimension you're multiplying on the tensor by. Okay, if you don't get it by now, it doesn't matter really.
We trust you.
There's a great survey article on this. It's cited in the paper. If you want to get sort of start with tensor, it's a paper by Calder and Bader. It's a great way to get started, and they have all of this explained in more detail. Okay, but it does take time some time to get used to it.
Oh, yeah, just to make sure that if my understanding is correct, you're assuming that M and C are fixed over time, right? The number of assets in each space.
So right now it's a balanced panel. Right, so that's I'll come back to that. That's the reason why I use mutual funds and not stocks, because if you give long times of stocks, you only have very few stocks that are alive for the entire sample. But mutual funds last longer than stocks, so I have a longer balanced panel. That's the reason why.
In reality, the shape of the tensor looks ugly, right?
So right now the data is a balanced panel without any missing values. I can talk about this if I come at the end, but that's sort of the picture you have in mind.
So what do you do with funds that fail or merge, or you just drop them, or?
I do, but it's the same thing with PCA. If you did this with PCA,
Yeah.
you would, in this way, you would only.
You kind of
the funds that are-
okay, I get it.
It's not any different
But
from.
when you go to the empirical results, I mean, there's a big sample selection bias from only keeping funds that are alive, right?
Sure, but that's true for PCA as well. We can talk about that later.
Okay.
on.
Well, there's like an EM algorithm
Yeah.
type thing that deals with missing values.
Yeah, I could, so right now I'm not doing that because, let's talk about this later on, okay?
Okay,
Yeah.
so matrix is just a slice of tensor. So if we think of that in that way, so what is the corresponding G for the
Yes,
2D?
so the way tensors can be described as fibers
Yeah,
or as slices. It's a different way to write a tensor. So a tensor is a collection of fibers and a collection of slices. Okay. So actually, if you write it in this way for 2 dimensions, this will be equivalent to the SVD.
okay.
If I did it in 4 dimensions, if I had a 4-dimensional tensor, this would just have another
Yeah.
fourth.
Yeah, I'm just trying to understand which is exactly being reduced in the 2D case.
So it's the same as the SVD, right? The only difference really is that this is now a core tensor, where in 2 dimensions, this is a matrix. And in 4 dimensions, this would be a 4-dimensional tensor, right? So the difference is that in the 2-dimensional case, the optimal SVD, this will be diagonal. That's why we have the same number of Ks here. Here, that's not necessarily the case. So we have a different number with K1, K2, K3. Yeah. So that's the intuition. notation, okay, so I just showed you this. This is the SVD in tensor notation. And this is called the Tucker decomposition, right? So we have a tensor, a large data tensor that will approximate by a lower dimensional object, right? And this is the error, approximation error. And this here is the Tucker approximation. Okay, so where G is, so I have KT factors in the first, KM second, KC third. So this is a core tensor, small core tensor, and that's multiplied by these three matrices that essentially expand the core tensor into the same dimensions as the data. So the intuition is that this core tensor corresponds to the H matrix, and these three V matrix play the role of U1 and U2. That's really it. And the rest, if you sit down and work out how this mechanically works, you'll see it, but it will take you a little bit of time. Yeah. So again, G is not diagonal, and the way, so let's say we pick this number of factors, then G and the V's are determined to minimize the error.
Can the elements of G be viewed as generalized singular values?
No.
No.
There are no singular values vectors. For tensors. That notion doesn't exist. So there's no eigenvectors, eigenvalues for tensors. Doesn't exist. So data compression, if I have time, I can talk about it too. So you can essentially count the number of free parameters and then sort of look at the data compression compared to the sample size. So similarities to the SVD, you can rotate both, so it's not unique. So the way it's usually normalized is that these U and V matrices are orthonormal, so they are orthogonal. The columns are orthogonal, and the norm is 1. Okay. So it's natural in the SVD because of eigenvectors, right? But in the tensor, that's how we also normalize these weeks. So I talked about this already. Okay. So obviously there's a closed form solution for the SVD, but closed form in the sense that we have to numerically compute the eigenvalues and eigenvectors. Right? So for the tensor model, you actually have to do this numerically. Okay, it's called, the most popular method is higher order orthogonal iteration. It's actually quite fast, it's robust, and I've never had a problem with convergence and so on. So I can, if I have time at the end, I can get questions, I can talk some more. I do run some Monte Carlo simulations to sort of get an idea of the estimation error, and it's actually very small, for at least 4 dimensions that are close to the data.
Can I ask another question? So I'm still trying to interpret these core things. So singular values, I think of their squares as variances or something.
So I will come back. So then
I don't know how to think about these guys. Like I don't have I don't have a box form.
So again, these are not singular values, but
Right.
they will essentially look like singular values. I'll come back to it in a second when I estimate in the data and I show you this.
Okay.
So for example, the first factors are always sort of range of means, just like in the PCA, same here.
First factors are, sorry, say it.
Related to means.
Related to
right?
means.
Typically.
Yeah.
Right? So the first factor is like long only, if you will, and the weights are roughly the same.
So you're saying it's like a positive thing,
Well, we can, yeah,
but that's not an artifact of tensors. That's an artifact of what's in the data.
right.
It doesn't
But
have
so
to be
most,
that way.
no, but this will be the case in the
For the
application here as
financial
well.
data that you see.
So we can also write this in factor form, right? So I showed the paper that you can write this 3-dimensional model as the sum of restricted 2-dimensional models in each of the dimensions. Okay, so you estimate the 3-factor models, and then you can back out the implied 2-factor models. Okay, so you just So instead of having to estimate all of these separately, right? So you estimate the three-dimensional structure, and the three-dimensional structure implies two-dimensional representation in each of the dimensions, okay? And they're restricted, and they're interconnected, okay? So that's an advantage of the Tucker decomposition. We can bring it back to the familiar two-dimensional representation. Okay. So data compression, I do it more on the data, but you can show that this Tucker model, if you have an n-dimensional, it's roughly, you compress the data roughly by q to the power of n, where q is sort of k divided by n. So the higher dimensions you have, it's more effective. So remember when I talked about the SVD models, I rewrote it to get a factor representation. You can do the same thing for the Tucker model. So the only difference is that this is now a vector. This will be a factor tensor, and this will be the loading matrix. So the difference between the factor representation in the SVD, we had a factor matrix multiplied by a loading matrix. Here in the tensor model, we have a factor tensor multiplied by the loading matrix. However, so this factor tensor it now has dimensions t by m times by kc, right? So this would be the two-dimensional version. This is the three-dimensional version. So this factor representation in the characteristic space reduces the dimension from C characteristics to kc characteristic factor. So one way you can think about this. This is the data tensor. I have T observations, I have M funds and C characteristics. And this factor tensor is T dimensions, T periods, M assets, but now only 3 factors. So if I wanted to back out the factors for a given fund, what would I do? Well, this is the T by 3 matrix for the first fund. So this would be the corresponding time series of my 3 factors for the first fund. So if I slice it vertically, this would be for each fund. This would give me the time series observations of the KC factors.
Okay. Can you, so I understand in 2 dimensions how you pick KC, you know, it's the Marchenko best or whatever significance. What's the intuition in this?
I'll come back to that.
Okay.
So that's the idea. Okay. So once I have this factor representation, then for each fund, I just pick the vertical slices, and this would give me the time series of the KC factors. Okay. And I can do it, this would be for all the funds, right? And this again stems from the 3-dimensional estimation, right? So essentially I expand here to the T and dimension.
So essentially, the factor models are different fund by fund or asset by asset. Is that correct?
So, for example, take the first fund here.
Yeah.
You have a time series for each of the characteristics.
Right.
These 3 factors would summarize the C characteristics in KC factors for the first fund.
But for fund number 2, it's a difference.
Yes, of course, yeah, I mean, so for fund number 2, you would, this would be the time series of C characteristics.
Yeah.
This would be approximate this to summarize the C characteristics. This would be
A different set from one.
Yeah, they're all different.
They're all
Yes.
different. That's,
Right?
that was
So that
clarifying, yeah.
these would be these slices would be approximations
Yeah.
to these, right? And so you
So,
the
yeah,
dimension, one second, the dimensional reduction here is from C to KC.
got it.
Right?
Okay. So, you know, a terrific application of this technology, we feed bond pricing, you've got literally
Yes,
tens of thousands of bonds,
Exactly.
and you have, you know,
exactly,
hundreds and hundreds of possible risk
exactly.
factors.
So I think there are lots of. There, I've looked, there are no applications in finance of this.
Yeah,
So-
that's interesting.
I'm taking the math off the shelf,
Yeah.
right? There's nothing new here.
Right.
Well, I think where I add something to this is I work a lot on the intuition because the engineers, they don't care about that. So the paper has sort of a lot of intuition how this relates to our two-dimensional case and things like that. But yes, I mean, every time you have a three-dimensional or high-dimensional data set, if you wanted just to summarize it, you can do factor analysis on a high-dimensional data set.
Mhm.
This, I mean, my experience, this works really well.
Yeah, so, you know, we built a bond pricing factor model,
Yeah.
bond by bond, so every bond had its own 12-factor model with 11 key
Yeah.
rate durations and a credit spread factor. This would be a great way of.
So you,
doing all.
here, if you do this, you
Yeah.
essentially run a two-dimensional PCA
Yeah,
for each of these matrices separately.
right,
So it's be bond one, bond two, bond three, bond four.
Mhm.
So in the two-dimensional case, you would do this for bond one, for bond two, and so on. However, obviously, these are correlated.
yeah, that's the
And if
matrix.
you do it separately,
Yeah.
then you
Yeah.
wouldn't use this. So this does the same thing.
Yeah.
But it uses all the information
Right.
together. So let's talk about this later on.
Yeah.
Okay. So that's the objective. That's the input that I will use for the asset pricing. Okay. Essentially now I will, once I have this structure here, this approximates the large tensor. I can use these three factors in the same, similar to any of these individual factors. So for example, I can sort, right, each quarter and so on, each time period. That's sort of the idea. So this is the implied factor form of the tensor model, okay? And essentially the mutual fund slices of this object here give me the KC factors for each fund. And that's what I want. Okay. So the intuition is, so let's call this is now a matrix. This is the matrix for each fund. So for each fund, this would be a T by KC matrix, right? So let's call this FTM. Then I will lose the C. So this FTM will be the KC factors observed over time for fund M. Okay, and this will be the input into my pricing factors later on. Okay, so they are summarizing the information in all C characteristics, right? But using information of the other funds too. Okay, so you exploit information across time, across other assets, and across characteristics. Okay, so there's no return information used so far. So this is so far not asset pricing, this is asset characteristic. Okay, and these then can be used to construct asset pricing factor. Right. So the idea is that this what I've achieved now is I have reduced the dimensions, but in the characteristic space and not in the return space. Okay. And again, this allows for complex interactions between the characteristics. So sorting doesn't give you that. Okay. Skip that. Some people are confused of what a time factor is, but about time at the end I can talk about this. Okay, so how about the application? So this I use a data set on mutual funds and ETFs, so active funds that trade mostly in domestic equities, right? So I roughly have 1,000, a little less than 1,000 funds, and against the reason I use mutual funds is because I get 34 quarters. It's not super long. But if I did the same thing with stocks, I would end up with a much smaller cross section of stocks. Okay, so I'm working on an extension how to deal with this for stocks. So my data tensor, 34 times observations, 934 individual funds, and 25 characteristics, so it's roughly 800,000 observations. And is this big data or not? I don't
No.
know. Right?
Small data,
But I mean, this applies to big data sets, right?
good.
So what I will do next, so I will estimate these models for different choices of these factors. Then I will construct these characteristic factors for each M, and then use these to form pricing vectors. Okay, so there's no formal selection methods for number of factors, so it's you know, I don't think it's what engineers really care about. They just, you know, try different things and see what works. So in the paper, I compare the fit of many combinations. I find it's stable in short sample, it's stable across time. I do subsample analysis, I do rolling windows. It's on the paper, you get very robust fits. And none of the results that I find really depend on the specific choice of these three Ks. So remember the dimensions of my data set is really asymmetric, right? I have 34 time series and 24 characteristics, but I have almost 1,000 funds. So here I have three examples. So the least parsimonious will have 10, 20, 15 factors. Then I have 8, 12, 12, 3, 10, 10, and 1, 4, 4. So this is the most parsimonious. Okay. So how do I compare models? This is the mean square error, and this is the implied R squared. Okay, if you essentially divide the mean square error by the variation in the data. Okay, so you can see that obviously the least parsimonious model has the highest error and the lowest R squared. Right, but even this model captures 85% of the data, and this goes up to 95% of the data. If you look at the data compression, so in some sense we compare the degree of freedom of the model to the total data sample size. This model here has a compression ratio of 99.5%, and even this model here is 97.3%. So these models here, they capture over 90% of the variation in the data, while having compression ratios of on the order of 99 or 98%. Okay.
So these are mutual funds. If you were doing this with stocks and doing it in the more traditional way with the two dimension, just to try and get more R squared is not necessarily better. Why is that? Because stocks have a lot of idiosyncratic return, maybe not so true for a fund.
No,
It could be,
so you might, I mean, for the same number of factors, you get a lower R squared.
but you might want a lower R
Yeah, I
squared.
mean, that's fine. I mean,
because
this is just comparing different models. I'm not saying that you need 100%.
No, I'm just saying in different
Yeah.
contexts, the best R squared could really depend on the data set
Yeah,
that
of
you're
course.
looking at.
Yeah, of
And
course.
here,
But-
I think higher is probably better than it would be for individual stocks, maybe, where there's a lot of idiosyncratic.
I mean, but
effects.
so, I mean, if you get a higher square for a very low dimensional structure,
Mhm.
right, that means that you can summarize information, right?
Yeah.
So it's the same thing here.
But that could
So-
be, it could be very period dependent. What I'm
Yeah.
saying is that the actual
Yeah.
true best model may not, at least in the ones I'm familiar with, correspond to the one with the best R squares.
Well, it depends on what the purpose is. Right now, I mean, this is your object, so your object, it's like similar with SVD. What is the best SVD is just given by the eigenvalues, right?
Well, but that's in sample. My goal is never to, I mean, I use in sample, but my goal is always to explain out of sample.
I will also do auto sample.
Uh-huh.
But again, this is very, very robust across time. So it turns out that the out of sample results are almost as good as the sample results.
Uh-huh.
So the nice thing is that even if you have very few time series observation, you still get a lot of information from the cross section. In the two-dimensional model, if you have a short time series,
Yeah.
then you get junk out of the PCA. So since here the identification comes also from the cross-sectional, even the model actually works pretty well for very short time series.
Are you familiar at all with the Barra models?
Yeah.
Because they like are all about cross section.
Yeah. So. Just to give you an idea of, so this is the MSE for now, this is by characteristics, and these are the different models. So the blue one is the most parsimonious, the light blue one is the least parsimonious. And here you can sort of see the improvement if you add more factors. Note that momentum and reversal are universal for all funds, for all cases are the have the highest errors. And note that especially if you increase, so if you have very few time series, so if the KT is very small, then you will really do not fit momentum and reversal. So in order to fit these, you need more higher KT.
What durations are momentum and reversal computed over?
So this is the usual same.
12 months.
Yeah, the usual.
Drop the first.
Yeah.
Count the first one, but are they the fastest moving
Yes, they are.
factors?
So in the paper, I go into more detail. So essentially, the more persistent a characteristic is, the lower the error is in general.
That would
Right,
make
so it's not
sense.
surprising.
Yeah.
Plus, this also depends on the correlations, and momentum and reversal have different dynamics, right? So it's not surprising that you need more factors to capture that. Okay. But for the other, for example, for the other characteristics, if you go from this to that, it's not a huge amount. Okay. So this is over time. So you can see these models, if you look at it's pretty stable, right? Aside from this first one. I will not get into this in detail. So the interpretation, I go in the paper, I go into much more detail. This is sort of the loadings matrix on the characteristics. So the first factor has only positive loadings, right? And then the others are long port. So this is like the mean, close to the mean.
Yeah.
And this, for example, would be going long in fundamental growth rates and short in price
So
ratios.
this is very consistent with this
Yeah.
paper that Alex Sopcich and I did, which is, titled what happens with more funds than stocks? And we did the dimensional reduction on the SED
Yeah.
on the universe of 15,000 funds,
That's right.
3,000
It's
stocks.
similar, yeah.
And we got the same thing. So the first factor was broad-based market, the second factor was a kind of a long, short, growthy axis, and then the third factor was interpreted as some sort of energy loading,
So this,
you know.
even though I do it in 3 dimensions, the interpretations of all the different pieces
Yeah.
are very similar to the 2-dimensional equivalent.
Yeah.
So, and that helps with the intuition, right? Because the structure of this model is actually quite similar to the 2-dimensional equivalent.
Mhm.
So just to give an idea, this is now the fit of funds for momentum, for individual funds, for momentum and reversal. This is the way I pick the fund is this is it's a 75 percentile fund across MSE. This is the 90th percentile, and this is the fund with the worst fit. Okay, so and these are again momentum and reversal are the worst case scenarios. So in some sense, these two cases here are 2 of the overall worst fits in the entire model.
Right.
So
Another question, Martin. So in these, when you talk about funds, you're including ETFs, which are typically tracking an index, and mutual funds which try to beat a benchmark, right? So, the ETF returns should be very simply explained, right?
if I take ETFs out, I get very similar
Okay,
results.
all right.
So it's not just different.
It's not, okay.
But I mean, these are the worst cases. So I mean, I was surprised that that the model, so the model is in orange and the data is in black. It's
Yeah.
not a terrible thing.
That's good.
And for the worst case scenario.
Mhm.
Okay,
Are ETFs particularly clustered in one area of the
I mean, most of the funds, so I come back later on when I look at different,
Okay.
many are cap-based.
Right.
Right, so it's,
Yeah.
and then you have the value funds.
Yeah, you also have thematic ETFs, which should be
So-
very narrow, niche.
Yeah, but they're few.
Yeah.
Plus, this data goes back to 2010, so
Yeah.
you have to be alive in 2010, so this niche stuff only came
Came later,
recently.
okay.
So they're probably not in
And
there.
stuff, okay.
They're very few, so there's I think one momentum fund in there.
Yeah. DFA.
So, okay, so this was the first piece. Now I have 20 minutes for the asset pricing piece. Okay, so far there was no asset pricing, so essentially I used this Tucker model to reduce the dimensions of this three-dimensional data set of characteristics, and I so pulled out these characteristic factors for each fund. Okay. So these are, again, these were the factor tensor, right? And then this would be the matrix of KC factors observed over time of fund M. So I would have capital M of these factor matrices. Okay. So these factors have also similar properties. So the first factor is related to means across funds and so on. So similar to the V matrix version. So here I will just concentrate on two models, on the two most parsimonious models that we saw earlier. So the 144 and the 31010. Okay. So I go in different steps. So the first step is I ask broadly, are these factors, these KC factors, related to fund returns, right? So again, so far, no information on fund returns. So there's no mechanical link to returns whatsoever. So the first thing I do, I regress excess returns, right? Typically, we regress excess returns on lag characteristics, but instead of using the lag characteristics, now I use my factors that come out of the tensor model.
And when you say excess returns, are these in excess of
The risk-free rate.
the risk-free rate? You're looking at active returns relative to the stated benchmark?
No, I'll come back to it later on. Well, this is right now it's just correlation, so it's not, so typically we use Formula Macbeth for this, but Formula Macbeth requires a pretty long time series, right? Here I have 34 observations. So I use parallel regressions with time fixed effects. I mean, it's pretty similar, but it works better for short time series, right? And I report entity and time clustered standard errors, and I look at the between R square. So that's the cross-sectional R square. After you strip out all the R square from the time series. So it's purely the cross-sectional, right? So now compare this to the regression where I use all 25 original characteristics in this regression. So this is the regression for the 3-10-10 case for the characteristic factors. So note first the R square is 50%. So this captures 50% of the cross-sectional variation in the returns. And for the entity clustered, I essentially get significance for 9 out of the 10 factors. For the time clustered, of course, since I have a very short time series, these T's are much lower. It tells me that the identification mostly comes from the cross-section, which is the way it is. So if I look at all 25 characteristics, so these are the 10 with the largest coefficients, you can see that most are actually not significant, and the R squared is actually lower, right? This has 25 characteristics, and this is 10 factors. So actually I get a higher R square for the 10 factors than for the 25 original characteristics. Okay. So this suggests that these factors actually are related to returns. Yeah. So what I do next, now I play the sorting game, right? So typically we sort on the C characteristics. Now I sort instead I sort on my KC factors, and I follow the exact same, the usual procedure.
So can I ask a question about the usual procedure? I mean, Paul and French did this.
I resample every quarter. I resample.
Yeah, but I mean, they do the top decile minus the bottom
That's what I
decile,
do
right?
here.
But for some things that that's not really an investable portfolio, right? And
So-
there no shorting costs, there no borrow costs.
We can talk about that. I totally agree,
Okay,
but, you know,
because I mean, I would say that the real test would be create investable factor portfolios.
my objective here is to essentially compare these factors to the Palmer French other factors, okay? I understand that this doesn't mean it's directly. investable.
We're in a practitioner hat, so.
Yeah, exactly. So the same caveats apply, and I fully agree with them, by the way, okay? So I end up with KC pricing factors, so from now on, when I say factor, now I mean pricing factors. Okay, so I get KC pricing factors, and here I get C characteristic factors, one for each characteristic, and I compare them to the Palmer French, and then I also construct the factors by characteristic. Okay, so in the paper, I also compute out of sample numbers, because so far, if I estimate the tensor factor model using the entire time series, I use future information to construct these portfolios. So instead, what I do is I start with a short window, and then recursively always add one more quarter to it and estimate the factor models each period, and then sort the next period. So these out of sample factors are not subject to this look ahead bias. And I do the same thing for the PCA factors. Okay. So just to look at some returns. So these are the 5 factors, the Tucker factors with the highest mean returns, and these are the 5 individual characteristics with the highest mean returns, right? So this sample is a little unusual, right? Because a lot of the classical factor over the sample period have been much weaker. Okay. So if you compare the Sharpe ratios, for example, they are uniformly higher than the Sharpe ratios of the factors based on the individual characteristics. Okay, so here's 0.89, 0.72, right? So the highest here is 0.46. And if I regress these factor returns on the market or the 3-factor model, you can see actually a lot of alphas are significant, while these alphas are not significant for the PCA factors. Yeah. Okay, so now linear factor models, right? All of these factors are excess returns, so I can run the time series, right? So for each fund, I run the time series, where little f now is a set of characteristic factors. So it could be Palmer French factors, could be the PCA factors, or it could be the Tucker factors. Okay, and alpha m is of course the pricing error, and I include the market in all specifications. So that addresses your comment. I could also first regress the returns on the market and take the residuals. Instead, I just include the market in all of the specifications.
Yeah.
Okay. So F always the first factor, and F is always the market, and then I add these other factors on top of that. Okay.
So how much of this is driven by things like SPY, which is basically the market, the correlation 0.9?
I don't have SPY.
Oh, you don't have it?
No, I don't. No, so
you had ETFs.
if you ETFs out, you get some results.
Okay.
Okay. So I'm going to report the most parsimonious case. It performs almost as well as this case. And in the table, so I compare root mean square pricing errors, and also compare. So if I, for example, have Palmer French factors in here, what happens if I add other factors? For example, the 2 Tucker models. So these are the R squared with the star, the factors plus other factors. Okay, and as usual, the GRS test rejects all of these, so that's a high hurdle. So this for benchmark, these are the 3, this is the CAP-M, this is for the SMB, and this is the 3-factor model. So let's focus on factors, models with 3 factors. So the root mean square pricing error is 2.6%. if, and the model, the Tucker factors, it's 1.91%. Okay. And for the PCA factors, it's 2.22%. These are in-sample factors. I'll show you the other sample in a second. So if you add 2 Tucker factors to the 3-factor model, you can see the model improves. If you include Tucker factors to the PCA model, the model improves. If you add these factors to the Tucker model, it might improve just a tiny little bit. So these are the out-of-sample factor. So here, the out-of-sample factor actually is slightly lower R squared, lower difference for crossing errors. You know, they're so close. I mean, that's no, I would not claim that this is significantly better than that. But it's on the same order, while the PCA out-of-sample factor do terribly, because if you have a short sample, right? Start with a short sample, PCA gives you jump. Okay, so out of sample, actually, this model works really well. Okay. So compared to benchmark models, subject to the caveats that I not mentioned, these models, these Tucker factors, so in this particular sample, I would not generalize this, actually do better than the benchmark factors. And again, I think the intuition is that these factors use a lot more information than the alternatives. So just to give you a bit idea about the pricing across fund types. So cap-based funds, balanced, growth, value, sector, and then there are a few others. There are not many, so you can ignore this column mostly. So if you look at the 2 Tucker specifications, they are better across the board. Okay, so it's not that they just fit one particular kind of fund much better than the others, but they are better across the board. Okay, so for all kind of fund categories, it's actually without an exception. So these 2 are always the best 2 models. Now, if you look at what kind of funds are priced the worst, sector funds have the highest pricing errors, you know, across these categories, which might not be surprising because they're probably quite heterogeneous, right?
Because they're wide, because
They do all kinds of different things. So, you know, growth funds do sort of similar things, but sector funds.
But this gets my early question, which is, you know, from a practical viewpoint, right? Say on UC Regents, they're over there in Oakland, you know, $60 billion under management. What they want to do is they want to pick active managers that are adding alpha. So you want to look at the return relative to the benchmark and then do this exercise to see if you can predict the alpha.
Yeah, I can, again.
That would be a great application. I mean, you've got all the data. So
Yes. This paper is already 85 pages long. Because I have to do all this tensor stuff.
paper too.
Yes. So one way to sort of think about this specification is, in principle, if returns depend on characteristics, you can ask whether a factor model capture the link between characteristics and returns. So if the model is correctly specified, pricing error should not depend on the characteristics. Okay. So if you request pricing errors on the characteristics, this B ideally should be 0 for all characteristics. Now, if I do this for average returns, 18 of these B's are significant. So 18 characteristics are linked to returns. And if for the Tucker pricing errors, it's 9 or 10. And surprise, surprise, momentum and reversal are fully priced. For the other factor models, they're essentially close to 18. So it means the pricing errors of these models still have information from the characteristics level. So they don't capture the link between returns and the characteristics really well. There's something missing. It's more unspecified. So conclusion. So this is sort of two pieces. One is the high dimensional factor models, right? How can we do factors style analysis in higher dimensional data. Right, so certainly in my application, this works really well. And then in the second part, the pricing factors that come out of this multidimensional factor models actually related to returns. And these tests suggest that this application is superior to the benchmark from a French and benchmarks.
Great. So just a couple of comments. I mean, I think there's lots of practical uses from this methodology. I think it's very cool. So we talked about fixed income, which is, I think, a really logical use of this. Then in terms of helping, managers select the funds or fund managers that do the best, looking at alpha versus just excess returns. Because I think a lot of the cross-sectional stuff is explained by the data on the market. And so it's sort of like, yeah, that's not really a fair comparison, right? That's not a practical thing.
Yeah, I can do that.
Yeah. And then the third idea would be that, getting back to my comment about following French factors being meaningless, that what we'd like to do is to find investable funds. So what you could do is take the characteristics, take this approach and apply it to ETS, which are investable. So for example, our broad market ITOT is 3 basis points. And you can short it, you can go long, and the transaction costs are basically 0. So that is actually an investable portfolio. So if you did it with the investable portfolios, then you could say, can these funds or alpha be predicted with these factor characteristics, which load on actual portfolios that you can be gone long or short. Yeah, I think it would be a nice application. So
One question, is there any practical guidelines of choosing the optimal size of the core tensor? For example, if it's too parsimonious, then the performance will be sort of.
So I mean, this goes back, essentially what I did is what everybody else is doing. I compare many different specifications.
But in practice, it depends on the actual size of my data if I want to use it.
Of course, I mean, I'm not saying that if I use for stocks,
So
this case would be different. I
my
mean,
question is there any rule of thumb?
I mean, it's the same as in PCA, right? You look at the spectrum of eigenvalues and you say,
look for the elbow.
that's it. There are 5 factors,
The kick,
right?
Right.
the elbow test.
It's like a bias variance trade-off.
It's similar, I mean, it's not really satisfying,
No.
but even the more formal criteria, they essentially just look at the spectrum of eigenvalues. So here you can look at, I do it in paper 2, I look at if you essentially you can look at which elements of the G tensor are really high, and not surprisingly, they're sort of on the diagonal. So again, this G is not quite diagonal, but the largest elements are on the diagonal. So that's similar to the eigenvalue.
Guys, we are totally out of time.
Yep,
let's
thank
take
you.
our- For the future, next week, travel schedules and holidays, we are not gonna have a seminar. The week after that, Shota Nishi is gonna talk to us from industry about risk, I'm guessing, I don't know this title yet. I will be away, but Bob Anderson will be hosting. And the week after that, Alex Skolnick, a probabilist and statistician and from UC Santa Barbara will be here, I'm guessing, talking about the scientific dragon, but we'll find out. So hope to see many of you.
Email me.
Yeah, that guy, yeah, or
Yeah.
Luther.
You have slides too, yeah.
Can we post the slides?
Yeah, of course.
We're
Yeah,
gonna post
yeah.
them on CEDAR
Yeah.
and your
Okay.
papers.
All students, don't take pictures, email the.
Yeah, email
Yeah, in
our
general.
seminar. Or look on the website, because we post, when we're allowed to, presentations, papers, and a lot of other cool stuff.
I just sent it today. That's why it's not online yet, but yeah, feel free to post it. There have been many applications of this.
Great talk. Really nice. Yeah, I think the fixed income.
Yeah, let's talk about that.
Yeah, it's, I mean, you could do it for fixed income. So the one of the stories you hear is like, oh, because